Okay. Hi everyone, I'm Chris Kanan, assistant professor here in CIS. And today our speaker is Professor Jie Qiao, who is probably already known to most of you. She'll be giving us an exciting talk on her cutting-edge research in optics and lasers. Dr. Zhao joined our department as an associate professor in the fall of 2013, and she has over 16 years of research experience spanning photonics, optics for imaging, and ultrafast laser systems. Prior to joining RIT, she spent 8 years as a laser system scientist at the Laboratory for Laser Energetics at the University of Rochester. But during her career, she has not only pursued basic research, but has had a lot of activities in entrepreneurship and startups, and has applied her skills in industrial settings. So Dr. Zhao has worked at 2 photonics startup companies, Grating Photonics and L&L Technologies, and one optics company, Optical, on various photonics devices, optical imaging, and metrology systems. And she earned her PhD in electrical and computer engineering from the University of Texas in Austin in 2001. She obtained her MS in precision instruments and fine mechanics from Tsinghua University in 1997. Did I say that one right? Tsinghua. Yes. And she has an MBA from the University of Rochester, concentrating in entrepreneurship, strategy, finance, and marketing, which I think is really cool. I haven't met many professors who have MBAs. Who also, I think it's neat. Anyways, she holds 2 U.S. patents and has authored over 50 scientific contributions and in national and international journals and conferences. So please join me in welcoming Professor Zhao.
Thanks, Chris, for the kind introduction. Hello, everyone. I'm glad to give a speech at my own department. And I have given a set of talks on such topics at different conferences. But actually, first time I was able to speak to my students at RIT. So the topic of my talk is on 3 subjects, covering metrology, optics for imaging, and ultrafast laser system and applications. And this is, as Chris has introduced, this is a combination of my 16 experience across photonics. At the beginning of 2000, including my PhD, as I was working on photonics for dense wavelength division, multiplexing for the anti-multiplexing for telecommunication. These you have seen are the diffraction grating based, the multiplexer and demultiplexer, fiber optical based devices, and waveguide based devices. This is the 8-channel wavelength, the so-called fiber to home are the demultiplexing and multiplexing different wavelengths. I was also working on silicon nitride-based ring resonator. That is the hot topic today after 12 years. And goes the circle. Then I move on to the optics for imaging, working for opticals, and the laboratory for laser energetics, where I was working on coherent phasing of large aperture optics, adaptive optics, optics for imaging, for detection of laser damage, and optical design and imaging. This is an example of uniform illumination, actually working with Bob Bonnie. He's sitting in the audience at the laser lab. And so I want to make a point that all the bases, actually the fundamentals apply to a large-scale laser system I work on at the Laboratory for Laser Energetics for 8 years. This is a 100-yard by 70-yard. Now, after I came to RIT, I confined everything back to my lab downstairs in the basement. This is everything on the optical table. But the knowledge, what I have used, the skills I have applied, they are all from all different sectors across industry, and from photonics, optical imaging, and ultrafast lasers. So the overall summary of my talk is that I'm going to present a demonstration of a novel optical differentiation wavefront sensor based on binary filter in the focal plane. We also create a deformable grating design with position optimized actuators, and propose applying the demonstrated coherent phasing and deformable technology to next generation telescope. Lastly, I will talk about the current developing in my lab ultrafast laser system, physical model, and process for fabricating the new generation photonic devices and for photonic integration. So the first subject is optical differentiation. For this project, we are working on high-performance wavefront sensing that is required by many fields, including lasers, adaptive optics for electronomy, about photonics, and we demonstrate a new optical, we call that ODWS. It's the abbreviation for optical differentiation wavefront sensor using far-field filter based on small binary pixels. We also design and fabricate this filter based on commercial lithography technique. And the current measurement have showed excellent consistency, accuracy, and repeatability. So the high-performance wavefront sensors are required by many fields, as I have mentioned. And primary is on the astronomical telescope field. You want to measure the star, but you have to go through the turbulence in the air. So you use a wavefront to measure that. Then, as a feedback from the wavefront sensing, use different mirror to correct the aberration in the atmosphere. This is the application in astronomical telescopes. In the laser industry, you want to get the finest focal spot. So wavefront is used to measure the laser beam phase front, then correct the wavefront. And another application is for optical component characterization. Freeform optics is a revolutionary type of optics, and we developed this wavefront target for freeform measurement. The internal ocular for the students who are interested in visions. Wavefront sensor can be used to detect the ocular aberration. And lastly is related to biomedical sensing called biomedical imaging. It can be used to detect the bio cell changes. That's the phase imaging aspect. Traditional sharp Harman sensor measure wavefront slope using a micro lens array. So for the students who are not in optics, the fundamentals of you have an optical wave, and we want to measure how the phase changes. If you sample the phase with a small lens slit, you actually see a different phase front with different local slope. And that's represented by this, like a wiggling line here. And you use a micro lens array that has multiple micro lenses. Each micro lens focuses the sample beam into a nominal position. But when there's a wavefront or phase front arrow, the centration of the focal spot is going to deviate from the nominal position. By measuring the deviation of the centroid, one can calculate wavefront slope. This is the principle. But the limitation of this technology is that the spatial resolution is limited by the micro lens pitch. That's about 110 micron. The second one is dynamic range. Because of the measurement area is about 110 micron, if you have large wavefront slope, you're going to see crossover and overlapping spots that limits the measurement dynamic range. And also, this is the micro lens array is chromatic lens. So there is a chromatic aberration. It could be problematic when you measure white light or polychromatic light. The signal-noise ratio is also limited by the number of photons per sensing area. So we want to address all these factors with a new technology. And so the technology we're developing is called optical differentiation wavefront sensor using a binary filter in the Fourier plane. The theory has been developed by Ward from University of Rochester a number of years ago, but the practical demonstration has never been well demonstrated because of limitation of this Fourier plane in the future. So we are first demonstrating using binary. So the concept for the first year student, you have Fourier optics. Is a straightforward concept. You have optical wave, you want to characterize at the input plane. So you set up a coax system, and you put a filter at the focal plane of the first lens. This filter has a linear transmission modulation for the fluence of the beam. So if you look at this mathematically, in the Fourier plane, if you add a linear transmission at the Fourier plane, then you use a second lens to perform inverse Fourier transform. The mathematical manipulation result is that it gives you the first order derivative of the phase to be measured. So this is the mathematical base for this. And the fluence function in the Fourier plane is a linear function changed from 0 to 1. When u equal to minus 1 over 2x, that's 0. And when u equal to plus 1 over 2 is x, that's 1. So by measuring the fluence in the far field, with filter, that's called F1. Without filter is F0. By doing the ratio of these two, you can get the wavefront gradient in one direction. By measuring the wavefront gradient in two orthogonal directions, one can derive the phase completely. So this is the interpretation using Fourier optics. You can also understand this based on geometrical optics. Different wavefront slope representing a different Chi-free angle going to the focus. You can see that the Chi-free angle is perpendicular to the phase front. But when they go to the focal plane, if you have a linear filter modulate the transmission, that means different Chi-free angle or different wavefront slope is going to see different transmission. And this transmission encoded intensity is going to be measured again by a camera in the image plane. That's how you use the intensity to measure the phase information. So we have the binary pixelated filters were designed using a spatial dithering algorithm and fabricated with a conventional lithography technique. So this is the continuous filter. We realized that by using a binary pixelated, you can see there's a statistical pattern with the opaque pixels and the transparent pixel. By doing this, we designed two sets of orthogonal filters, horizontal and vertical. It's one pair. To perform a self-consistent test, we also designed a 45 degree and plus and minus 45 degree. These two pairs should give us the same result if the design is correct. And then we have a reference beam. This goes through 100% as to simulate without filter situation because we want to make sure the optical partners is the same. So we have set up an optical setup in my lab downstairs, and the setup is our goal is to measure the light for monochromatic light, also for polychromatic light. So the monochromatic light the light coming from a Heine laser going through a spatial filter to expand the beam, and then it go to the input plane. This is the someone has another one? Okay. So I'll continue. So this is the input plane to measure the wavefront to be corrected. We have the first full F system, first lens, and the second lens, the filter is in the focal plane. We also set up a traditional Sharp-Harman sensor to as a gold standard to compare the measurement from our ODWS sensor versus Sharp-Harman sensor. In combination, we have a decoupled white light decouple white light source to perform the white light measurement. In order to perform freeform measurement, it's very expensive to make a freeform object or to actually generate freeform. So we use a deformable mirror that has in the same image plane as an input wave plane. The deformable mirror was used to generate a freeform surface, so we can quantify the accuracy for freeform measurement. So this is the basic setup. So a future the first generation ODWS, the reason I call it first generation because the pixel size of the filters are 10 micron. This is our starting point, not so expensive compared to a high resolution sensor that costs about 50K. Xianghua knows the price from Imagine Optics, 50K or 60K. This sensor probably less than $1,000. So the first measurement, we use the deformable mirror at a relaxed state. That means without voltage. And we measure the wavefront. Thank you.
It's the middle button.
Okay. We measure the wavefront, use the 0-90 filter and the plus 45 and minus 45 degree. This is the measure the wavefront. But then we look at the difference. The difference is a 1/50 wave. It's identical. So we got exactly the same result as we expected by using this wavefront design. So this is the first order self-consistency check. This is the filter actually used. This is the 0-90, 45 and minus 45. Then we compare against the traditional Sharp-Harman sensor measurement. As shown in the setup, we have a Sharp-Harman sensor as gold standard. So this is the measurement of the wavefront generated by our 1.5 meter lens at the input point. So we have a known wavefront. We know what's expected. This is the expected wavefront, the work of Zach. Expected wavefront of this much for both sensors. Then this is the measurement from Sharp-Harman sensor. This is a commercial available sensor. This is the sensor we developed. When you look at difference, our sensor, OWDS, actually deliver a higher accuracy compared to the Sharp-Harman sensor. Both of them, they are very close to the expected value, but the OWDS present a higher accuracy. This is for monochromatic light. We further perform the measurement for polychromatic light using a white light source. This is again the first column represents what is the expected wavefront, and second column, the first one is measured by Sharp-Harman sensor, and the bottom one is measured by our sensor, OWDS. And we again get a better accuracy compared to what is being expected for both monochromatic light and polychromatic light. Then we look at the signal to noise, repeatability of the measurement. So the way to look at the repeatability of the measurement is that we conduct more than 15 frames of measurement. Then we look at the RMS of each measurement. Then we look at how much variation from each sensor. Overall, our sensor has delivered better repeatability compared slightly better than the Sharp-Harman sensor. But the other issue is that in terms of measure astronomical telescope as astronomical aberration, the light level, in many situations, you're hungry for light level. So when the light level fluctuates, you really want to get consistent measurement from your sensor. So in this measure, we keep decreasing the input light level from 100% to 6%. Then we want to compare which sensor fluctuates more. And again, this is the OWDS. Our sensor, this is a commercial sensor. Our sensor fluctuates less than the commercial sensor in terms of when you decrease the light level. So we're very happy with the current results. So we also build a numerical model to conduct Fourier transform and also incorporate the binary filter to predict the future performance of next generation design. So this OWDS has the potential of measuring freeform optics, and this has been numerically demonstrated. So we generate a freeform with x to the cube and plus x squared. This is a freeform wavefront. Then we look at what we can measure numerically with a continuous filter versus a filter that has 2.5 micron. 2.5 micron is realizable with the current lithography technique. Then we look at the wavefront arrow. The measurement arrow with a 2.5 micron should be on the order of 1/50th wave. So we are very confident that we'll be able to measure freeform optics. So our next step is to, we already did a design for the 2.5 micron filter, and it's in-house, it's delivered. We're going to perform a freeform measurement with our setup. So the conclusion for this project is that we demonstrate the optical differentiation wavefront sensor using far-field-based smaller pixel binary array. It show excellent consistency, accuracy, and repeatability. And ODWS poses a high potential for application to astronomy, lasers, freeform metrology, ocular and biological cell imaging. This is the where we can get money, many places. And for future work, we want to demonstrate, perform a demonstration of measuring freeform surface is underway. We have the deformable mirror. We have the technique to generate freeform surface. We have the 2.5 micron pixels. And the OWDS application to ocular and biological cell imaging will be investigated. So I'll be happy to discuss with anybody who has the ability to provide biological cells. So I want to see the phase change from biological cells, microscopy application. So the second project I'm going to present, this is a totally different but related subject, is on the deformable optics design and coherent phasing. The overall take-home message for this project is that the lightweight meter-scale deformable optics are required by astronomical telescopes and high-energy lasers. This is a drive. So we have conceived a new deformable grating-based compressor that's used to compress high-energy short pulse laser pulses, and realize an actuator position optimized design. We have demonstrated a coherent phasing of half-meter scale diffraction gratings, and taking those demonstrated experience, we have developed a proposal to NASA with an interdisciplinary team from multi-institutions to investigate the application of coherent phasing and deformable optics to astronomical telescopes. So just a little bit of background for the people who are not familiar with high-power laser. The meter scale grating compressor is required to meet omega EP. That's where I worked before, and that's how I started this project. The intense pulse needs to be first stretched and then propagate through the amplifier. That's a big block of glasses, so the glass will not be damaged. And during this propagation, at the end of the amplification, you have an optical subsystem called grating compressor. It consists of two pairs of identical diffraction grating. The major function is to aid dispersion to compress the laser pulses. But in order to prevent the laser damage, it requires a meter scale gratings, and nobody in the world can make this. So either you make a thin glass, you have a lot of surface deformation, and you have to correct that, or you have to use multiple segments to make large meter gratings. So there are two solutions. So what I'm presenting first is using a deformable grating to deliver this 1 meter optics. So we built a spatial temporal optical model to predict that can predict grating waveform, that the phase arrow surface deformation on each grating actually can lead to a temporal pulse broadening. This is the profile of the grating waveform. If you have about 1.5 wave grating waveform arrow, that's going to lead a spatially broadened pulse. The Fourier diffraction limited size is about 2 micron. That can be broadened to about 16 micron. And in the time domain, when you think about laser pulses, you not only think about in spatial domain. You also need to think about whether all the light come at the same time. That's called short pulse. And the pulse length of our laser is about 500 femtoseconds. That's like 1 femtosecond 10 to minus 15 seconds. Very, very short. So any broadening, this is already a factor 2 broadening from the Fourier transform limit. That needs to be corrected. That means we won't get a bias focus. So I have proposed a deformable grating architecture using a thin substrate and multiple actuators to mitigate waveform errors. And after so the concept of this work is also multidisciplinary. It's a combination of mechanical, finite element analysis, and the optical design. So finite element analysis was used to determine the influence function of actuators of a deformable optics design. So the idea is that if you look at the surface deformation from a surface, that's in relation to the Young's modulus, that's the material property, and the stress in each direction, and Poisson ratio. Poisson ratio is when you change the component in one direction and how much the other direction will change. How much that change with the temperature, that's just a linear equation. So we have built this model in ANSYS that is able to predict the influence function of this deformable optics. Influence function meaning that when you change one actuator, how the surface change. So you generate a multiple matrix, each matrix for each actuator. So this is called a control matrix. By knowing the influence function of all the actuators, by knowing the input waveform you want to correct, one can determine how much each actuator needs to move. This is called the control matrix. And so this is the full closed loop. We generate this, then we load that into optical model. In this design, for all the people who have mathematical background, you can see the application of math and physics into optics. So we use a design called, we design a model, integrated MATLAB and ANSYS model, to optimize actual location using a genetic algorithm. Genetic algorithm is that you first have an initial design, and then you generate children of this design. And the children who have the best genes, they are going to recombine and evolve. So this is a very you can use MATLAB to do that. I actually work with a high school student and then take an undergraduate student, and we were able to demonstrate this optimization process. So the initial design and boundary condition will be set up by you. Here is by me, and then from there, the genetic optimization is going to generate a population of actuators with a randomly generated. For each population, the previous introduced ANSYS finite analysis model is going to generate surface shape for each configuration. For each surface shape, we're going to see whether we have achieved minimized wavefront error for each surface. And this will just go and go until you achieve your merit function. So the result of this, the optimized design achieves a focus pulse that is spatially diffraction limited and temporally Fourier transform. And you can see that there are two columns. One on the left is the initial design. You see the numbers 1 to 9. These represent the location of the actuators for the initial design. And the first one on the right represents the locations of the actuators after optimization. They are drastically different from the initial design. If you look at the final wavefront, corrected wavefront, we have achieved at least a factor of 4 better than the initial design. And in terms of the focusing, we have achieved both spatially and temporally focused pulse in the far field. So this work, we just published this work last September in Optics Express. And there are some interest from the large aperture grating manufacturing and also from the large laser facility. And it's very applicable to astronomical telescopes. So in combination with that, we also have demonstrated a technique using interferometric near-field timing technique to have 2 grating segments. So if for the students who do not have the optics background, if you want to build a 1 meter optics, but you only have half-meter segments, and you want to put them together, but they have to function like one piece. And the way to test that is using optical interference. You probably learned that from the graduate optics course from Professor Sportlander. And so you do interference across 2 grating segments. I show you this setup. So the beam coming from laser, one beam goes through is going to be reflected by the back surface of transmission flight. The other beam goes to the diffraction grating and reflected back by the refraction flight. And these 2 beams will interference. When they interference, you see 2 sets of interference patterns. Then you analyze the relation between the 2 sets of interference. And the way to analyze that, this is the Fourier optics, Professor Easton's course. And you can see where that can be applied. So you do a Fourier transform in a Fourier plane. You analyze that. You take the DC signal away. You analyze the AC signal. In this first order AC signal, that has the phase information. After you perform inverse Fourier transform, you will be able to derive the phase information of the optics you are coherent phasing. And by knowing the differential phase information, you do a feedback. This is a closed loop feedback to control the actuator in the back of the grating segment. That's how the gratings are aligned. This is a fundamental principle. Involve optics interferometry, optical control. This is the result. So the coherent phasing technique has enabled Omega EP to operate as the only tailored loop picosecond laser user facility since 2008. And I don't know how many shots they have done. I think last year at least like 4,000 shots. So this figure shows that if without the coherent phasing of the segment grating, you're going to get a larger focal spot. Because I just asked my students, when the optical beam is smaller, without a coherent phasing of the grating segment, you're going to have a smaller beam the larger focal spot. It shows right here. But if you have coherent phase, the 3-segment grating, you get a much tighter focal spot to perform physical experiments, plasma physics. So this is the end result. It has a high potential for European extreme light catered to 10 petawatt laser. I have been connected to work on that if I have the capacity. So the potential application to astronomy is to coherent phase large aperture diffraction grating for large aperture telescopes. So this is the proposal, the base of the proposal I have worked on, I have done. Using diffractive optical elements, provide a lightweight and folded solution for the next generation telescope. So the grating is, this is what you see is a piece of membrane, but it is a grating. So you can make grating on a piece of membrane. The membrane only has a thickness of 25 micron. This can be done by etching method. And if you use a membrane to build telescope, you can build much larger aperture because of the payload limitation, the current payload limitation. You cannot send unlimited weight to space. So compared to current state of art, this is Speeder telescope, Hubble, and James Webb under construction. If we can use transmission diffraction grating based on membrane, this is the 20-meter telescope we can build. So this is target for next generation telescope. And the basic principle is you use segmented diffraction optical element to build a primary to much lower the weight of the telescope. Because of the grating are dispersive, different wavelengths are going to focus at different locations. So my students learn about chromatic dispersion. And you have to use a second grating to correct that. And I think I have taken Jacob Worth and another student in my optical system design as a course. He was also contributing to the proposal writing on this part to understand how you coherent phase those two segments to remove the dispersion effect. So the reason I started this proposal is I went to a conference, I heard this talk, and the Ball Aerospace got a big DARPA project for $39 million called Marie. And the mission was to build transmission grating-based telescope to perform imaging. So they were able to demonstrate single segment imaging. This is the scene corresponding to approximately 1 kilometer by 1.4 kilometer ground scene, as seen from the GEO orbit. And this is what they have seen with one single segment. Pretty good imaging. But they were only able to demonstrate there's one segment, and they failed at coherent phasing. And I talked to them, I share with them what I have done for the laser industry. They said, oh, this is perfect. We just need this technique. So that's how I actually connect with Paul Aitchison. He was the former PI on this project. So we start developing this proposal. Then I need a science mission. So I connect with the Professor Joe Kessler, and start working on this proposal. So we have proposed a project to NASA to investigate co-phasing approach for DOE telescope, and to leverage the demonstrated experience in coherent phasing control and adaptive optics. And the proposal proposed to model and also build a laboratory demonstration of coherent phasing of power delivery segments. So in this proposal, we have built a cross-institutional team with the scientists from Ball Aerospace, from NASA Goddard, Lawrence Livermore. Jerry Britton actually is the person who designed this membrane-based grating. I connect to him right away, and he said, I can ship you one piece of grating. And Ted Morley from Precision Optics, Excelos. And Nextop is a company that actually makes the membrane. So that's NASA ARPA proposal is where I proposed, but that's a very, very competitive proposal. We probably need to propose a couple times rather than going through a very big budget, doing a smaller budget to get things started. So the potential application is persistent for the students who are interested in remote sensing. This can be applied for persistent observation You know what I mean? And laser communications, and Earth LiDAR to the Earth when you look down. And when you use the different spectrum to build the diffraction grating, you can also to use this to do exoplanet observation, target a different spectral band. This is the potential application. So for this project, we have demonstrated a lightweight, meter-scale deformable optics design. We demonstrate coherent phasing of half-meter diffraction gratings. We developed a proposal to NASA, target for application in astronomical telescope, next generation LAB telescope. So the last project I'm going to talk about is the one I'm very excited about. It's the ultrafast laser for photonics fabrication and additive manufacturing. So my objective in this area is to develop laser systems utilizing the laser background and the optical imaging background, and the physical process for photonic fabrication and additive manufacturing. And we have so far built a numerical model to optimize laser parameters and control thermal effect of the laser processing. We have also demonstrated initial laser processing of silicon carbide, and additive manufacture parts. We won some external funding from NSR and ONR DoD through Optical system. We built interdepartmental collaborations with professors Rich Houston here, and David Ross from math, and Vinny Gupta from the material science, Dan Kumi from industrial engineering. We also built a strong industrial partnership with Corning, FPG Photonics, Ultrafast system, Optical, carbide glassine, and nanowire. The NASA is also an instrumental partner for this project. The bottom line is we have submitted a proposal. You have heard about this in Photonics. It's a $600 million funding. Rochester is part of that. We have proposed pre-proposal, and I will talk more about that. So laser radiation can offer flexible forming and polishing of optical elements and for additive manufacture part. Optimax probably is interested in this. So the fundamental principle is that you do raster scanning with a laser beam on parts you want to polish and you want to make a form. And from Harvard Laser Institute in Germany has demonstrated laser polishing for silicon glass. They also publish curved lenses with CO2 lasers. And this is in comparison with manual polishing on freeform optics. This is freeform optics. This is the new generation optics. But because of the form is irregular, people have to use manually to polish that. That completely undo the benefit of having freeform optics because of the cost, the time, and the complex process. So we want to develop a technique using laser polishing that can be integrated with the current optics fabrication techniques. So the other application is to polish waveguide and add mirrors for photonics integration. Zhaolin probably is interested in that part. Pulse laser polishing with decreasing pulses width has been shown to produce smoother surface. There are different mechanisms. When you hear about laser, there's continuous wave laser. There's nanosecond laser, there's ultrafast laser. When they interact with the material, the mechanism is all different. For CW laser, you purely melt the material. You change the state of the material from solid to liquid, then resolidify that to smooth material. For nanosecond laser, it's still through the heat effect. There's a heat wave, a shock wave. You interact with the material. For ultrafast laser, it's a much more complex physical process. But when we talk about laser polishing, we are using the laser ablation, the direct ionization part of the physical process. When you talk about laser welding, that is multi-photon absorption, the ionization, and plasma formation. And that part, then there's a thermal effect. So the current literature has shown that when you lower the pulse width from nanosecond to picosecond, 100 picosecond, you get a smoother surface. And this has been demonstrated on metal. We want to work on glass or transparent material. The ultrafast laser radiation can be used to write 3D photonic waveguides and while transparent materials without an intermediate absorbing layers. So photonics, light, they are three-dimensional. The current way of making chips, silicon chips, they are two-dimensional. But light is three-dimensional. It has polarization. It has more angular momentum. It's not just current or voltage. So you need to have 3D structure. So ultrafast laser, in my view, is the next generation. It's a revolutionary tool to make 3D photonic structure. And this is a demonstration. People use ultrafast laser to make photonic lighting. Professor Jordan probably knows about this. You can actually couple beam from multi-mode into single mode. And this one can actually relax the imaging requirement because you do the point imaging already by using fibers from different spatial location to map into another spatial location. And this is a new demonstration from Lehigh University. And a group of scientists has demonstrated this last year. This published in Nature. It's a waveguide, crystal waveguide using grating by ultrafast laser. And the Germany, from the Harvard Institute, they have demonstrated using ultrafast laser for welding of different optical elements. So this is a highly interdisciplinary area, research area, across lasers, optics for imaging, photonics, material science, and control. So I think my experience across disciplinary actually perfect suit me for this area. Because you need to have a grasp which direction to go from each direction. So we need to understand, first have the understanding of laser material interactions, understanding of waveguide properties, otherwise you cannot make valid waveguide. You don't know what to write about. Then internal generation of type and control for focusing is enormously important to write photonic structure, be able to control and manipulate light. So our experience with beam profile wavefront control, I have just presented with the two previous research threads applied to this area. Spatial polarization modulation, temporal pulse shaping and chromatic dispersion management, and control and spatial temporal coupling. This is all related to the ultrafast laser field, and also optics for imaging. And the optical metrology, there were someone didn't know about optical metrology. So I think I should explain that. Optical metrology is basically an instrument or a method to measure something. When I talk optical metrology here, I talk about optical method to measure optical wave, or to measure, sometimes you measure the distance, you measure the profile. It's just a measurement methodology. So optical metrology for characterizing the fabrication process and performance. And this is the imaging side, optics for imaging side. So that's the room, a lot of room, and you can ask my students, Zach, where he applied his Fourier optics, where he applied his image process. In terms of the physical process, I try to make it simple. The determinist laser-based fabrication requires very good understanding and control of the complex nonlinear interaction process. So the gist of this, that's why I want to work with students from physics. And I got one, Ryan Scott. And I want to work with more physics students to tackle this. So the gist of this is that whole interaction process can be dominated by nonlinear process. It's a combination of nonlinear and linear process. But for ultrafast laser, like refractive index modulation to wide waveguide, or for welding, it's start with the multi-photon ionization. When the electron receives enough energy, it's going to go from the valence band to the conduction band. So you generate free electron from the photon, from the ultrafast laser. Once the electron gets to the conduction band, it continues to receive photon energy. Once it receives photon energy exceeding the band gap, it's going to generate another electron. And that electron is going to drop to the valence band to have more ionization. And this whole process iterates. You are going to have multi-photon generation, ionization. When the ionization goes to a certain level, you're going to have plasma formation. The plasma formation is going to cause material breakdown. It's going to generate this welding and index modulation. And you can also see the void. So to control this process is not easy. They require very good understanding about this physical process. Well, thanks to my students, they do have this physics background and imaging background, so we can tackle this from multiple angles. So a femtosecond laser ablation system was built up in my lab to carry out laser polishing of optical material. And this laser was from Amplitude. It cost about 300K. I didn't have the money to buy it, but Xianghuang knows that we work with this company. They know my work in the laser field, so they loaned me this laser for a month. We were able to demonstrate all the experimental results so far. We demonstrated with this loan laser. This is a 400 femtosecond laser with a wavelength of 1030. You can change reputation rate from 500 kilohertz to 2 megahertz. That has average power of 20 watts. And we have a translation stage with computer control. So the initial experiment demonstrated very effective material removal of silicon. Well, thanks, Jordan, gave me that piece of silicon. So that's where we were able to demonstrate our silicon result. And the estimated volume removal is actually pretty significant. It's in the millimeter region. The removal depth is about 10 microns. And I showed this data to my collaborator at NASA Goddard, who works on actually lasers, and they do polishing for silicon. And he was amazed by the effectiveness of this laser ablation for silicon material. So we were happy with that, but we also see some unexpected effect. Rather than removing material, we see material pile up on the side of the ablation. So we wanted to understand what caused that and how to affect that. So now the material aspect comes to play. I have a visiting scientist, Jie Qiao, and he is in material science. So we were able to use working with Professor Rich Hilton, doing SEM EDS measurement that show the presence of oxide at material catalog. So by measuring the spectrum of material, we were able to compare the measured area, the process area, with the unprocessed area that shows our increased peak for oxide. So we know there's oxidation occur, but we also suspect there is a material melting as well. So the energy, the neutrality was energy dispersive X-ray spectroscopy, and we verified the oxidation. Now so the goal, the next step, actually, we continue is we want to understand how this oxidation happens from the numerical modeling point of view. How do we predict that? How do we avoid that? How do we have a controlled process? So that's necessary to understand the surface temperature evolution in ultrafast ablation was predicted using a numerical model. And this diagram shows the flow of the interaction. You have an impinging pulse that has a Gaussian profile, and with a Gaussian profile energy. And with the deposition of the laser pulse, you have energy increase, and there's a direct relation between temperature and energy. It's related to the material density, thermal capacity, and volume. And this temperature rise causes a heat accumulation, and then there's a heat dissipation process. Now this is material science and thermal part of the understanding. So the ultrafast laser deposits a special Gaussian distributed energy which induces steep temperature rise. And this energy can be represented by a Gaussian pulse centered at x of Cn, y of Cn. That's directly related to the temperature. And the heat induced by ultra-short pulse laser dissipates through the material over time and space. So this is the differential equation we have to solve to understand how the temperature changes with time with space. But when solving this equation, there's a complexity because the thermal property also changes with temperature. So this is the equation Lauren has to solve. When we have multiple pulses, the heat is accumulated over time and space. When a repetitive pulse laser is scanned across the material, you can see that when a pulse deposits on material, the instantaneous temperature rise, and then the heat dissipates. Before it dissipates to the base level, another pulse came. So there's a repeating process. So the heat is there's actually a heat accumulation process. But at the end, you're going to see an equilibrium because the time for the heat to accumulate is equalized with the time it takes for it to dissipate. So we use a central finite difference method to handle the temperature-dependent material property in heat dissipation. So this is the where you use your differential equation. My student often ask, why do we need to learn all the math? So every time I relate to them to a practical problem they can solve with that piece of math. So the model results indicate laser parameters induce high surface temperature above oxide threshold in silicon. So by plugging the laser processing parameter 10 micro pulse energy with a 2 megahertz repetition rate, 1.5 millimeter scanning speed, and 70 micron focal spot, we were able to see that only after 4 pulses, the surface temperature has exceeded oxidation temperature, that's 700 degrees. That's why we were seeing oxidation in our material. And then this model enabled the optimization of laser processing. Lauren has presented this work at the SPIE Optifab to over 120 people as her first presentation. I thought that was pretty good. So in continue, by optimizing the repetition rate, the material melting and oxide growth can be avoided. So we continue with the model, develop an optimization process to vary the repetition rate, vary the scanning speed. So we construct a matrix to develop an optimized laser parameter to have determinist laser processing. And thus you can see that if we operate at 1 megahertz, we're going to exceed the oxidation temperature. We're going to very close to the melting temperature. But when we operate at 500 megahertz, we are much below. The relaxation temperature is much below the oxidation temperature. At 100 kilohertz, the temperature is completely relaxed to the initial temperature. So we come back to the thermal regime. So now we have a controllable process for laser processing. We can remove the artifact, we remove the melting, remove the thermal oxidation. Then the next step, we're going to tackle the probability for the multi-photon absorption and ionization, and to continue to understand how we can control that aspect. And Corning is very interested in that, so we are building a collaborative agreement with them. So in my lab, the established, as I have said that, the ultrafast laser processing is very costly set of research. It costs about $600K to build up this ability. So the establishment of the ultrafast laser facility, so far, we were able to obtain about 180 leverage of the limited stock funds through the building strategic industrial partnership. So we have obtained the commitment from industry for about 350K in-kind equipment contribution with like 4 places. So this amplitude laser committed 220K toward the purchase. So we could spend 140K for 360K laser. We further collaborate with LAC, and this beam shaping and optical scanning system can be in combination with a laser system. And Optical has generally donated us as in-kind support a 3-axis control system. So this is not a free meal because they see the value of the research. I actually made a visit to 8 companies And if you want to become a professor, be prepared. Go on the road to present what you can do. The spot ablation, it shows with this, we were able to demonstrate the ablation on the true steel and silicon and geosilica. These are also in collaboration with Harback. They provide additive manufacture part. From metrology part, is also very expensive. We were able to build the metrology secure also through collaboration with Nanovia. It's a California company. We got 50% in-kind support. We got IPG laser for free loan to us for 6 months. All these are very hard work compared to the theoretical modeling is equally hard. And fortunately, we have Professor Rich Houston, his SEM lab. We were able to characterize the material, collaboration with Vinny Gupta's material lab. In terms of modeling capability, we have my students building off-frame modeling. That's Laura and Ryan. We have console, multi-physics modeling, Frank and ZMAX and LabVIEW. This is our computation ability. So in conclusion for this part of research, we have built a numerical model to optimize laser parameters and control thermal effect. We have demonstrated initial laser processing for silicon, silicon carbide, and additive manufacture parts. We actually won external funding from NASA and ONR. And I think most importantly is the industrial collaborators from the glass company, from the equipment company, from laser company, from the metrology company, from government on the NASA, the other side, and Center for University, free from optics. So I was at the Photonics meeting, the first national meeting yesterday, with all the players coming to Rochester, actually RIT. And I brought up the laser welding, and the comment from the participants that this is going to be a breakthrough for photonics fabrication. They say it's not this can be, this will be. That's a word. That person actually correct that. And I truly believe this is going to be a revolutionary fabrication change for optics and photonics, for the ultimate integration. And so in conclusion, we have demonstrated with all three research thrusts I have established at RIT, we demonstrate a novel optical differentiation wavefront sensor based on binary filter in the focal plane. We have created deformable grating design with position optimized actuators. We are developing ultrafast laser systems, physical models, and process fabrication technique for novel 3D photology fast threading, material winding, polishing. And the goal is for the ultimate functional integration of photonic devices. So I'd like to thank my team. The ultimate goal of Off-Frame Lab, the vision is to provide coherent, integrated, closed-loop research education experience to directly engage students from all levels. So I want to point out that all the students come to my lab, they learn something, they take away something as well. And you can see that I start with the first two graduate students. There was no table, optical table. And the first undergraduate I took, there was nothing on the table. And I gradually, this is RU students coming last summer from Wheaton College. First year graduate student, Anthony, we start building. Actually took a high school student, Matthew is there. And he did a fabulous work on the signal noise characterization between the two sensors. And I hired a postdoc for summer that actually speed up the research working with our undergraduate student, Zachary. Zachary has done a fabulous work on the experimental demonstration. You have seen the results for accuracy measurement. These were all done by Zachary. And I have a collaborator, Christoph Dora. He represents Activate. They did an in-kind support on the design on the filter side. And on the laser side, my team includes Lauren Taylor. She's a third-year student. Her first paper is under review by me, and with the differential wavefront sensor is currently being reviewed. And Jie Qiao is a visiting scholar in material science. Rand Scott, physics student. I'm very glad having him join my team. And Yilin Dang, he took my geometrical optical course, and now he's working on the project. Daniel Morgan, he was a NSF R&D student, and this is also worked for me for 2 months. He's a faculty at another university now. So I want to thank all my sponsors, especially at the beginning. Every little support, I'm very grateful from the funding from NASA, CIS, Optical, and the internal funding, that's my startup. And these are, in my view, are equally important compared to the cash I got, because these are the blood food for all the experimental demonstration I can perform. For the equipment I got from nanoclear Lassie, amplitude, Optical, and imaging optics, Activate. That's all I have. Thank you. Hey.
You as far as optical material removal, I saw you had induction. You're going to propagate energy through radiation. The temperature is going to go way high. I didn't see that in your model.
We're not there yet. So we're only at a small fraction of this modeling process.
Oh, okay. So you have shocks and also the equation of state at those high pressures and temperatures is kind of...
We are going to have that, yes.
Yeah.
Yes, that's under consideration. Right now, we're building that part of the model. It's not an easy problem to tackle. Hey, Doug.
Do you plan on commercializing the optical differentiation wavefront sensor?
Yes, I am. If there is a company called Numerous, and they want to visit my lab, they're very interested in commercializing that. If your company is interested, I will be happy to discuss. I think it's really, well, I'm biased. I think it's really good technique.
Have your experiments been all done in vacuum?
No, that's why we have oxidation. So at the beginning, I wanted to work in vacuum. Then I thought about in industry, the worst thing they want to work in vacuum because they want to work in an environment that is not constrained. So I started tackling this oxidation problem because I can control my laser parameter. It's ultrafast laser. If I do the parameter correctly, I understand the physical process correctly, I can operate in air because it's such a short time scale. Yes?
I understand the ablation for doing the polishing or making the surface structure, but for inside material you show waveguide, so what's the mechanism for making a higher index material inside of a solid where all you can do is change density?
Oh, you can change the refractive index.
Okay, what's the mechanism for that?
So when you change the, it's a heat. It's still the heat. When you add a heat into the material, there's going to be a phase change. Actually, the phase of the glass actually change. Then you're going to have different refractive index. But the modulation depth is different for different glass material. Yes?
So could you use some type of coating to approximate working in a vacuum so that you don't have the oxidation problem?
Some type of what coating?
Some type of just coating so that there's no exposure to oxygen.
I want to remove material. So I can
remove material, but could you be working in like a temporary coating? So like a liquid coating that has a lower third order properties so that the photon interaction wouldn't happen in the coating, it would happen in the silicon still.
Well, that's interesting. Well, I don't know what type of material can sustain the heat. So you have to search for the right material. But that's a good, reasonable idea. Yes.
How much slope can the optical differentiation sensor handle? Your example was pretty flat. It was only maybe less than a wave.
Yes.
How much can it actually handle?
So we have a second generation with 2.5 micron. How much slope the wavefront sensor can handle is determined by the filter size. So this first generation, our filter size is only 2 millimeter. Our next generation will be 2 centimeter. So we will be able to handle about 100 radians per millimeter.
Okay.
Well, there's no more questions. We're about 10 minutes over, so.